What's up, bitches? Today we're going to learn the Rankine cycle, okay? So this is what it's going to look like. You start at point 1, it goes through a pump, that's the boiler, then it goes through your turbine, and then finally in the condenser and it restarts, okay? This part, you don't really need to know this by heart for your exam. What you do need to know is the TS diagram. That's the most important part. So I'm just going to draw that real quick. For a simple Rankine cycle, this is what it's going to look like. These are your saturation lines, okay? Whatever is on this side. Oh, what the fuck? Why is it? Never mind, let me get blue. Whatever is on this side, whatever is on this line, it's saturated. It's a saturated liquid. Whatever is on this side of the lines, it means it's saturated gas. Okay? By the way, for this Rankine cycle, you're working with water, okay? So, usually, your simple Rankine cycle, it's going to start at a certain saturated liquid. Step 1. Then, once it goes through the pump, you're going to raise the temperature, ideally at the same entropy. Then it goes up like this into the boiler. Step 3. And then, back to step 4. And then back to step 1. Okay? This is what your cycle looks like. Wherever you see a straight vertical line, that means work is being involved, okay? For a Rankine cycle, work out is over here and work in is over here. Wherever you see like these curved lines or honestly like anything that's not a vertical line, there's heat being involved. For a Rankine cycle, heat comes in from point 2 to point 3 and heat leaves from point 1 to point 4. Okay. For a Rankine cycle, generally, unless your problem states otherwise, from point 2 to 3, it's constant pressure. I'm just going to write CP. And 1 to 4, it's also a constant pressure. That's it. The equations you have to know is work is equal to specific volume times delta P. Some questions you're going to have to use this equation. But otherwise, you just have to use delta H, okay? Depending on which point you're evaluating. Same thing with Q, delta H. Whether it's Q in or Q out, you just have to change what H's you're using, okay? Keep in mind that these values always have to be positive to make sense. If it's not positive, that means like, oh, you fucked up the order. One last thing, thermal efficiency, it's equals to W net divided by Q in. W net is equal to W in minus W out. You can also use this equation for some questions as it might be easier. And that's it. That's your simple Rankine cycle. Now, for reheat Rankine cycles, it's going to be a little bit different, okay? It's going to start at the same point. Step 2 is also the same. Then, it goes up to step 3. Next, it doesn't go all the way down like in your simple Rankine cycle. It's going to sometimes land over here. Sometimes it's going to land down here. I'm just going to draw it over here. Okay, you just have to pay attention to your question. Then it goes back up over here, step 5. And then it goes back. 6. That's supposed to be a straight line. Here is constant pressure. Here's constant pressure. And from point 4 to point 5, it's supposed to be constant pressure. Okay. Again, wherever you see a straight line, that's where work is being involved. Okay. So work out is this straight line over here, 3 and 4, and between point 5 and 6. Okay. Here we see another vertical straight line. Wherever it's a vertical straight line, it means work is being involved. Here's W in. Q in is over here, step 2 to 3, and over here, between 4 and 5. Wherever you see curves, it's heat being involved. Q out is from point 1 to 6. Whoops, Q out. That's it. That's what you need to know for your reheat Rankine cycle. It's the exact same thing. You just have to pay attention to your question, okay? Whatever is... Wait, let me redraw it over here. Okay? Again, these are your saturation lines. Whatever is outside the saturation lines over here, it means that it's superheated water. Whatever is inside this saturation line curves, it means that it has a certain quality. Okay, So you would have to find the, well, this is the equation. It's HF, no, sorry. H is equal to HF plus the quality times HFG, okay? You would have to use this equation if 0.4 or usually 0.6 also, it's going to be within these curved lines. And that's it. That's your reheat Rankine cycle. It's super easy. One last thing. Sometimes you're going to have multiple reheat things. You're going to have some shit like this, okay? But the principle is the exact same thing. It's just with extra step. And that's it. That's your reheat Rankine cycle. All right, let's do a problem just so we could practice, okay? Over here, consider a steam power. Well, I'm not going to read the whole thing, but it's basically we're dealing with the reheat Rankine cycle. So the first thing that you do is you draw the TS diagram. So not only you're going to get partial credits for this, but it also doesn't make you look like a complete retard. So step 1 over here, step 2 over here, goes up like this, 3. And then for step 4, it's saying that there's a mixture quality at the end of both turbine exits, okay? That means it's going to be within the curved lines. 5, then 6. And that's supposed to be a straight line. It's also giving us the pressures, okay? The boiler at 4 MPa. Reheat section 0.5. And condenser at 10 kPa. Okay. Next, it's asking us for temperature at the inlet of each turbine. So that's T3 and T5. And it's also asking us the thermal efficiency. So the way you start this is you're going to want to have to write P1, T1, P2, T2, P3, T3, P4, T4, P5, T5, and P6, T6. Some questions you're going to have to use the temperature. Here we don't have temperature, so we don't need it, but it doesn't matter. Just write T just in case it's like easier for you to follow, okay? So first things first, step 1, it starts as a saturated water, and we have the pressure, okay? It's given over here, 10 kPa, and P6 also is given, 10 kPa. We have P2 and P3, 4 MPa, 4 MPa. And then the reheat section from step 4 to step 5, it's the same, 0.5, 0.5. That's it. We have all the pressures, okay? So if you look at your table, we can find the values for 0.1, okay? As you can see over here in the water cycles. I'm just gonna, not the water cycles, the water tables. I'm just gonna write it out. For your reheat Rankine cycle problems, you want to copy down. What's important is your H, your S, and specifically for 0.1, your specific volume. You don't really need the specific volume for the other points, but you could just write it down just in case, but you just need it for 0.1. Once you have all of these values, keep in mind that over here is Win. So we're going to have to use this to find H2. Win is equal to your specific volume times delta P. Usually you're going to use this for step 1 to 2 only. And a lot of reheat Rankine cycles, they use this. Okay. So we're going to use 0.1, 0.00101. And delta P is between 10 kPa and 4 megapascals. Okay. You have to, since the work is being calculated in kilowatts or kilojoules per kilogram, you have to take kilopascals. Okay. So that's 4k kilopascals, negative 10 is equal to work in. Okay, calculating this, we get a value of about 4.03. Okay, next, we also know that the work being done is equal to H2 negative H1 or H1 negative H2. I don't know. Okay, so we already have H1 over here. So plugging this in, we get H2 of about 195.84. Perfect. 95.84. That's it. You don't need to find S2 or whatever for 0.2. We just really need to find the H's to calculate the thermal efficiency. Next, we need to find T3. That's what the question is asking. Okay. So you read the question again. It's asking that the mixture quality at the exit is 90. Okay. So H is equal to HF plus XHFG. So at 0.4, we know that the pressure is 0.5, okay? So you check your tables again. You check the 0.5 and you just have to plug in the values, okay? The numbers right here. So I'm just gonna write it out real quick. Evaluating these values, we get a H4 of about 2,537.29 H4. Okay. So let me just write it down. What was it? 2,537 point. Fuck, I don't have room. Hold on. 0.29. You're gonna want to do the exact same thing for the S this time. Okay. So S is equal to SF plus X SFG. The reason why you want to do this is because, as you could see over here, 0.3 and 0.4, their temperature changes, but the entropy is the same. That's why you want to find S4, okay? So, plugging in the exact same values for the table, we're going to get this formula right here. And evaluating this this equation that we got here, we get S4 of 6.325. Okay. You write it down over here just so it's easier for you to follow. S4 is equal to 6.325. All right. We know that S3 and S4 from your table over here, it's the same thing. 6.325. So, and another thing, we know that it's outside the curved line. That means that it's superheated. So, with a pressure of what was it? 4 MPa, right? 4 MPa. And an entropy of 6.325. You check the tables. And basically, you have to interpolate to find your H. And for this question, it's asking for the temperature. So to find the what was it? The enthalpy and the temperature, you have to interpolate using these values you see in your table over here. So the interpolation equation is, what was it? Y equals to Y1 plus, what was it? Y2 negative Y1, X2 negative X1 times X negative X1. Using the values you see on the screen over here, you just plug in the values to get this equation over here. You're going to get this formula at the end, okay? Keep in mind that you're using, for over here, I wrote X's, but basically you're using your S as a reference point to interpolate, okay? And that way you can find both T3 and H3, okay? H3, I wrote it out over here, okay? But it's the exact same thing. You just have to interpolate, okay? Where you're going to, once you evaluate those, you're going to get a value of H3 equals 2939.9 and T3 of about 292.7 degrees Celsius, okay? So we're going to write that in our table. 292.7. H3 is equal to about 2939.9. That's it. You're going to do the exact same thing with 0.6, okay? Because you see here that 0.6 and 0.5, it's the same S, it's the same entropy. So, we know that the pressure is equal to 10 kilopascals at 0.6, and the quality is equal to 90%. So, you go to your tables, you go to the pressure equals 10 kPa, and you copy down the exact same thing. H6 equals to HF plus X HFG. Reading the table, we could find these values and we just plug in these numbers. Plugging in the numbers, I'm not going to write it all out, but once you plug in the numbers, you're going to get H6 of about this. And you also need your S, okay? So we're gonna write this out our table on top. Whoops. Whoa, 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 whoa. H6 about 2, 3, 4. Whoops. 4.7. S6 of about 7.4. As we can see over here, 0.6 and 0.3, it's a straight vertical line. The S is the same. So here we know that S5, sorry, equals to S6 equals 7.4. Finally, for 0.5, you do the exact same thing. You interpolate again. You have a pressure of about 0.5 megapascals and an S of 7.4. Since it's outside the curved lines, it means it's superheated. So what you do is you go to the superheated tables and you interpolate. Okay, so again, H is equal to H. Well, I'm not gonna write it down. It's the same shit over here. Y equals to Y1 plus Y2 negative Y1 times X negative X1. You just follow this interpolation equation to find your H, and in this case, the temperature. Plugging in the numbers and interpolating, you should get these results for your fifth point. Okay, so finally, we're gonna write that in our table. H5 is equal to 30.93, and the temperature of 283.7. All right. Just keep in mind that T3 and T5, they're not exactly the same, okay? They're not exactly like supposed to be in a straight horizontal lines. That happens sometimes, but it's okay. So we found these two. Now for the thermal efficiency. There's two ways of calculating. We could find the work done or the Q in, Q out. Okay? I'm just gonna use both ways, okay? So let me just move over here. I'm gonna write it down over here. W net divided by Q in. Okay. W in is equal to over here. Where is it? H2 negative H1, which is all over here and over here. We have the two values. Plugging in those two numbers that we wrote on top over here and over here, should get an W in of about 4.03. Okay. Now W out, it's these two straight lines over here. Okay. So it's equal to, where is it? H3 negative H4. The difference between these two. Plus this straight line over here as well. H5 negative H6. Plugging in the values that we wrote in our table up top over here, you should get a W out of about 1088.84. So work net is equal to work out negative work in. Since we found these two values, it's going to give us the result of about 1084.81. Okay. Now we have this. That's our work net. Q in is equal to this curved line over here, okay? So H3 negative H2 and this other curved line over here. Keep in mind, wherever you see a curved line, that means heat is being involved, Q. And wherever you see a straight vertical line, work is being involved. Okay? So for a Rankine cycle, Q in is on whatever is on top. So H3 negative H2 and H5 negative H4. Plugging in the values that you wrote in your table over here, you should get a Q in of about 3237.7. Q out is at the bottom. It's just H6 negative H1, which is about 2152.89. So thermal efficiency is equal to 1084.81 W net divided by Q in, 3237.7, giving us the result of about 33.5%. You could either use W net divided by Q in, or 1 minus Q out divided by Q in. It's going to give you the same result, but that's how you solve a repeat Rankine cycle. Thank you for watching.